All right, so this is number 48 in the homework. Well, this is number 7 in the homework, but number 48 in the textbook, and it's all symbolic manipulation. So this ones like this can be kind of tricky. We've got a block of mass M down a smooth slope. Well, it's smooth-ish in the sense that it has a very small coefficient of kinetic friction, which we're going to call mu sub k. And let me see what else. Just to double check what the other variables are in the problem. Just want to make sure I get it right. So from a height h and length L, okay, length L, so that'd be the hypotenuse. So h, oh yeah, this one, expressing it in terms of h and L can get kind of tricky. So let's go through the, let's go through the derivation, because they want the height is h and the length is L, and so we've got final speed v, and we want to find v and express v in terms of h and L and m and probably g, accelerating downward. So what's the free body diagram look like in this case? Well, it's only 3 forces, but it can be a confusing one. So let's work in a coordinate system where the x-axis is along the direction of motion and the y-axis is perpendicular to that. And we want to find, obviously, we want to find the acceleration, because once we have the acceleration, then you can just use the kinematic equations to find v. That's really what we're trying to do. So, but in order to do that, we need to know what all the forces are. And so let's draw the forces. We've got mg straight down. Now we have an angle right there, but and then this is the normal force, and this is the friction force. That's the friction force is what's going to make it tricky, because without the friction force, the answer is pretty easy. It's just, without the friction force, the final speed is just square root 2gh actually. But since we have the friction force, now we have to do a little bit of these square roots. So, and we know that F net points that way, down that incline that we established. So let's sum the forces now. In the x direction, which is the one we're interested in, we've got mg. Now, I'm not going to write h and L right now. For now, I'm just going to make up the angle theta, which is the arc sine of h over L, because L is the length of the incline, h the height. That's going to make this theta as well. So we've got mg, plus mg sine of theta, which is the x component of this mg vector right here. Now it's going to be minus the friction force, and that's going to equal plus the mass times the acceleration. And once we know the acceleration in that direction, then we'll just plug it into the kinematic equation. The issue with this example is that what's the friction force? Okay, and from what you've read in chapter 6, the friction force is equal to the given coefficient of kinetic friction times the magnitude of the normal force. Just some brief comment about this equation. The friction forces and the normal force are always perpendicular. Okay, so you could say that F sub k is the dot product of F and N are 0. They're always perpendicular, and they're always acting along the direction of the incline. And so, right, and so that is the expression relating the two magnitudes. I don't really have a good expression for the cross product of them. Yeah, not sure. But they are perpendicular, so we need to find the normal force. Now, how do we find the normal force? That's from the y equation. And so the y equation is plus n minus, it would be mg cosine theta, which equals 0. So the normal force then is equal to mg cosine theta. So that means the friction force is equal to mu mg cosine theta. Again, I'm sticking with theta, but eventually we'll get into expressing it in terms of the H and L. And if you're wanting to work ahead, you understand all this, try and express cosine of theta in terms of H and L. You'll get a square root there. And you'll end up with the final answer will be a square root inside a square root. It's fine. So the friction force is equal to mu sub k mg cosine theta. And so you can plug that into the x equation. And so the x equation becomes mg, let's see, it becomes mg sine of theta minus mu sub k mg cosine of theta, and that equals ma plus ma. So then the acceleration that we measure in terms of the thetas, which will convert at the end, is a equals, you can even factor out the g of sine theta minus mu cosine theta. At which point we'll have plugged that into the kinematic equations for the x-axis, because it travels a distance of L. And so that becomes, I'll just save this and just clear my board and write a new one. I'll post what we're doing, these slide, or post these strains to our Blackboard. So that means that the kinematic equation was v final squared. The velocity at the bottom is the initial squared, which is 0, plus 2 a delta x, which in the picture is just L. And so really the answer is that v equals square root 2al. But that is certainly not what mastering physics will accept, because we have to express our acceleration in terms of H and L. We had it just derived that it was, I'm going to write the square root at the end, 2g sine of theta minus mu cosine theta L, all square rooted. I'm not following the chat, by the way. So, and then now we have to remind ourselves what these H's or what these thetas are in terms of H and L. So going back to our picture, we've got theta right here, H and L. And so sine of theta is the easy one. It's just H over L. But then the cosine theta, you need this third part, which is square root L squared minus H squared. And then so the cosine theta is that square root over L. So let's try to write it out. There might be some cancellations that take place. We'll get 2g h over L, right? Minus mu sub k, don't forget the k subscript, right? Times cosine theta, which is square root L squared minus H squared over L times L. And again, that's all square rooted. And so the L's cancel, looks like, and we're left with what we would expect, actually, which is 2gh, right? What the velocity would be if there was no friction, minus this extra correction due to the coefficient of mu square root. Oh, actually, let's put parentheses in front of the h. 2g h minus mu square root L squared minus H squared, all square rooted. And you should plug that into mastering physics and get it right. If the coefficient is 0, if the coefficient of kinetic friction is 0, like I was just saying, then this second term goes away and you're left with square root 2gh, which would just be the speed of the mass. Notice how it doesn't depend on mass, by the way. Square root 2gh would be the speed of the mass if it was on a smooth surface, which actually it doesn't matter what L is, no matter what the surface is. We could have done this. I mean, we could have made it a sharper surface. We could even make it like a curved surface. If the surface is smooth, the final speed after it's gone down the height h will all be the same. And that the fact that we're recognizing that is actually a precursor of energy, which we'll be doing in a couple weeks. So does anybody have any questions or comments on this example? All right. Number 7, so that was number 7 on the homework. Hopefully you guys in person actually got set up. So that's a good question. Number 48. Anybody have any other homework questions? I mean, I can go through some more problems that, you know, it's really what everyone's preference is. I have some really basic problems that folks might like to review. Or, I mean, if you folks also want to, we can just select harder problems like this. It's whatever your folks' comfort level is. Does anybody have any preference?
Could you go over number 5 on the homework?
Yeah, sure. Just remind me what it is. What number is it?
6.52.
Ooh, sounds like Sam on the ice sled. Yeah, it's a snowy day, and you're pulling a friend along a level ice, whatever, or road on a sled. Blah blah blah. You've both been taking physics, and so you wonder what the coefficient of friction is. And so there's a story that you have to read. What have we got? You've been walking at a steady 1.5 meters per second, and the rope pulling up, let's see, at 30 degrees, at a 30-degree angle. Are we given the tension? You estimate the mass of the sled with your friend is 60 kilograms. All right, you're pulling with the force of 75 newtons. What answer will you give? So let me see if I got it all straight. Again, these are numbers in the textbook. And so, okay, so draw a picture as usual. For the person that asked the question, is there anything specific you want me to address, or just kind of jump into it?
Just jump into it.
Sounds good. Well, I'm going to draw a picture because that's the first thing that you do, just to verify that you know it. And that doesn't have to be a dramatic picture, just stick figures will do. Yay. There's the rope, 30 degrees. Okay. Oh, and the speed is a constant, 1.5. Does the speed matter in this case? No, it doesn't. All that's important in this case is that since it's steady, they like to use this word steady, a steady 1.5 meters per second will give a 0 acceleration. Okay. So that automatically activates Newton's first law. So this is really another equilibrium problem. Let's draw a free body diagram. Let's start with Y. Hopefully you're drawing the free body diagram with me. So the force, then you start with gravity. And you know that the mass, let's see, what all do you know? I mean, you can even write down all these knowns. You know that M is 60 kilograms. You know that T is 75 newtons. Theta is 30 degrees. And you're trying to find the coefficient of friction, mu sub K. And what else do you know? You know that the acceleration is 0. Okay, so let's write the forces then. We've got mg down, gravity. And this, we also have a tension up and to the right. And we know that magnitude, T at angle theta. Okay, but we have normal force up and then friction backwards. So F sub K. And all those add to 0. So that's free body diagram. What is the sum of the forces? So now that we have the free body diagram, we can sum the forces like usual. So we'll do it in the X direction and in the Y direction. If you're trying to find, okay, yeah, we're trying to find the coefficient, that's right. So this one, actually, you don't need to do everything. No, actually you do, yeah. Let me see, let me show you why, because you need to know, in order to find the coefficient is the ratio of, if we're doing absolute values, it's the ratio of the friction force to the normal force. And so you actually need to know both of those in this case to find the answer. So we're using the free body diagram to find both the friction force and the normal force. So let's write it down. Now these both equal 0. So that's not bad. So in the X direction, we have T cosine of 30 minus the friction force equals 0. Right. And then in the Y direction, we've got plus N minus T sine of 30 minus mg equals 0. So I'm just going to estimate these off the top of my head. In the Y direction, what's the normal force? Well, sine 30 is a half, so that one's an easy one. If m is 60, then the mg is 588. I just know that. And so the normal force should be, well, normal force is T sine theta plus mg, which should equal, yeah, 75 sine of 30 plus 60 kilograms times 9.8 meters per second squared. And you get whatever 588 plus 37.5 is. 588 plus 40 is 628. So 624.5 is the answer for the normal force. This will be, so the normal force is 624.5 newtons. Now everyone's numbers might be different. Now what about the friction force? That one's in some sense the easier one. The friction force is just going to be T sine or T cosine 30. So T cosine 30 is 75 times radical 3 over 2. And that is I don't know off the top of my head. If you give me like a minute, I could probably come up with it, but you should get about 50 or close to 60 actually. Yeah. Anybody in the chat want to tell us the answer? Whatever 75 times cosine of 30 is.
I got like 65.
65. Okay. Yeah, that's actually going to be, that's fair. So it's about 65 newtons. So then the coefficient is going to be u sub k equals about 65 newtons over about 624.5 newtons. That's going to be about a little over 0.1, maybe around 0.11. What are the units of the coefficient of friction? Well, nothing, because it's units of friction divided by units of normal force. All right, so 0.11. And yeah, if you look in the textbook, we've got the coefficients of friction for different materials. I could pull this up real quick. I think it's on the slides, and share with you what estimated values are. Like I said, give me a minute. Let me find them. Slides have so much extra stuff in them, but I don't want to, things kind of bogging us down. I mean, we can do these problems if you want. These like quick check questions. There's a lot of quick check questions. That's one thing that's fun to do over Zoom. Just looking for the table of friction coefficients. Is this it? Yeah, here we go. Sorry, question?
Yeah. Why did
You're echoing, but what's your question?
uh why did you do t sine 30 as negative? Because wouldn't it be going with the normal force?
Let's see, did I mess that up? Right here.
Yeah.
Yeah, okay. So that's going to mess this up. So instead of being, so yeah, thanks for catching that. That was a mistake that I quickly made when I was getting in a hurry. Yeah, there's an error with the signs. It should be in the direction of normal force. So you're correct. This is two positive signs. So that was my mistake. And so that's going to make the normal force 588. Yeah, so in this place, then it's going to make the normal force mg minus t sine of 30. Oops. And so that's minus. So instead of 624.5, it is 588 minus 37.5, which should be 551.5. Yeah. So I get, so the corrected value for this, I mean, everyone's probably got different numbers, should be 551.5. Yeah. Which of course changes the friction force, and so, or which changes the coefficient. And something more like 0.9. What I was going to say is that you should expect to get a number of about 0.1, because in the textbook, there's this table of coefficients. And I fortunately found it right here. So the friction coefficients, if you look here, this is for like car tires, wet tires, steel on steel, blah, 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 wood on wood. We tend to use wood on wood a lot for different problems. Wood on snow, about 0.06. Okay, so, and of course, ice on ice is going to be a lot smaller than that. Some of those rolling friction coefficients don't even make sense. They'll just be too small, and rolling there might not even be enough static friction for rolling motion in some of those cases. But yeah, we got about 0.06. I mean, for our problem, we probably got about 0.1 or so, just so it's around that value. Good. Any other homework questions that people want to try? These are certainly problems in the sense that they are pretty difficult. You know, the exercises certainly are going to be easier, but I'm happy to do more of these problems if people want to. I think it might be good practice. But it'll just take me a minute to find one that I think is good. Let's see. Did you guys have to do 49? Kind of similar. Oh, okay, yeah, 49. Let's try 49. Sam, whose mass is 75 kilograms, takes off on level snow on his jet-powered skis. The skis have a thrust of 200 newtons and a coefficient of friction of 0.10, just like I was saying. Unfortunately, the skis run out of fuel after 10 seconds. 1, what is Sam's top speed? And 2, how far does Sam travel when he finally comes to a stop? And this is like, how far has Sam traveled? So this is the total stuff. So yeah, let's do 49. Has anyone looked? I forgot if this is actual homework question or not. I do this example a lot, but okay. But let's do this one, because this one is a good one to see the connection between forces and kinematics. So, unfortunately, there's not a whole lot of angles in this problem, so we can just do the problem like normal. Okay, so I'm gonna save this. And let's try 6.49. For those of you that are, if these problems that we're doing are a little overwhelming, I do have another video that I recorded for some more basic problems. And so just the more practice you get, the better. So in this picture, we have Sam, you know, so now I get to just draw a stick figure, right? Okay. On his skis. And so at time t equals 0, let's just make a basic coordinate system. And so what's going to happen in this case is that at time t equals 0, he's going to accelerate. And then that's for, I forgot what it said. I think it said 10 seconds. He's going to be at some displacement x1, and then he's going to continue with a negative acceleration until he comes to stop at x2. So, you know, be as careful as you want to when making up this picture, because you've got 2 accelerations and you've got 3 different locations, x0, t0, v0, x1, t1, v1, and then x2, v2, and t2. And what we're trying to find, x2 really, really it's x2 minus x0. But if I were you, I would set the origin to be right where he starts. That way, what we're trying to find is x2. So it's kind of like the sprinter problem, except there's not a top speed, there's just an acceleration. So free body diagram for the first part. We've got the thrust force, and then a small normal force, mg down, and then a friction force backwards. Fortunately, we don't have to fuss around with coefficient or with angles. That's F net that way. Okay, so we'll need to find this acceleration from this diagram. And then for this one, we will need to do the same thing. But the only thing different is now the thrust force is gone. So the normal and the mg's and the frictions are all the same for the second part. Right, so let's give ourselves some space to work. Just double checking that there aren't any other questions or comments. Let's see. Oh, someone else did number 5, or number 6.65. Yeah, I'll get to that after this example. Good. Thanks for all these homework questions. All right. So for during the launch, let's call it the launch, right? We've got in the x direction, the thrust force minus the friction force equals the mass times acceleration. Okay, and this is kind of shorthand because, again, this problem is kind of assuming that we've had enough practice to where this is easy to write down. And in the y direction, we've just got n minus mg is 0. N minus mg equals 0. Coefficient, let's see, what do we know? I'll write what we know up here. We know that the coefficient is 0.1. We know the thrust force is 200 newtons, I believe. Mass is 75 kilograms. Let me just double check all that. Okay, just to be clear, where's the number at? Ah, here it is. Okay, so 200 Newton thrust force, 75 kilograms, 10 seconds, coefficient 0.1. Good. Okay, so this is all right. And so what's the acceleration then? Okay, so this is how these problems work. I mean, you have to usually use one equation to find something for another one. In this case, we need to know the normal force, which is, yeah, in the y direction, normal force equals mg in this case. So the normal force equals 75 kilograms times 9.8 meters per second squared. What is that? 75 times 9.8 is actually a rare one that I don't know. 80, so 70, it's 686. 58.8, 68.6, 78.4. 73.5 or 735 newtons. All right. I just did that in my head. Yes. Right. Yes. 58.8. So 588 and 686 and 784. Yeah. Okay. So that's the normal force. So the friction force is going to be, that's easy. That's just going to be coefficient, kinetic friction times the normal force, which is 0.1 times the normal force. So it is 73.5. Okay. So what's the acceleration then? Now that we got the friction force, plug that back into the x equation, and we'll get 200 minus 73.5, 200 newtons. thrust force minus 73.5 newtons. You can do this in your head because 200 minus 75 is 125. And you're going to add 1.5 to that. So this is 126.5. So the net force in the x direction is 126.5 newtons. And so the acceleration is, yeah, if it wasn't for that pesky G 9.8, this would be a lot easier. Oops, sorry. So the acceleration is, acceleration is A equals, A sub x, A sub 0 really, A sub 0 x, because it's the first one, plus 126.5 newtons divided by 75 kilograms. I don't know that. So that's something that you have to work out. It should be about, obviously, 1.6. It's very close to 1.6, maybe like 1.61. Let's say around 1.61 meters per second. Or sorry, not 1.67 meters per second squared. Right, 1 to 6.5 divided by 75 equals, and what's the answer that I get? Okay, I actually got 1.70. Oh, that's because I mistyped. 126.5 divided by 75. Okay, 1.68. Okay, so that's the acceleration in the beginning. While we're here, let's just do the acceleration after the launch or after the fuel runs out. So this is, I'll just go up here. So during the stop, do we need to rewrite all the forces and the whole diagram and everything? No, we can just say that the acceleration is now just the friction force divided by the mass. Because once the tension goes away, or sorry, once the thrust force goes away, it's just friction force. So the friction force, like we said, was 73.5. So this is minus 73.5 newtons over 75 kilograms. Oops, it looks like I'm about out of space, doesn't it? So that's going to be about 0.98. So that acceleration is then going to be about a sub 1x is minus 0.98 meters per second squared. These are really good problems. So yeah, now we have the accelerations for both cases. And then we'll need to know, so now it's a dynamics problem actually, or now it's a kinematics problem. We've used the forces to find the accelerations, and now we can use the accelerations to find all the other kinematic quantities. So I'm going to save this. Just to do the kinematics now. And we're trying to find out the whole distance, that is from start through the acceleration, A0 and then V1, and accelerating with A1 back to rest. So we're trying to do the whole thing. So I would just do, what's the easiest way to do this? Well, we know this is 10 seconds. There's a delta T of 10 seconds. And so that x1 minus x0 starting at rest would just be 0 plus 1/2 a0 t1 minus t0 squared. So 10 seconds squared is 100, so it's 50 times 1.68. So x1 then will equal, right, because t1 minus t0 is 10 seconds. So 10 squared is 100, divided by 2 is 50. So we had acceleration of 1.68. And so this ends up being 50 times 1.68, which is 84. 84 meters. Yes, it's 84 meters. Which, how did I do that? I just looked at this and I made it, I just made this 168 divided by 2. You know, because this is equal to 100 times 1.68 divided by 2. So just, that's easier to do than 50 times 1.68, in my opinion. That's the first one. How fast are we going though? We'll need to know that V1. V1 equals 0 plus 1.68 meters per second squared times 10 seconds. That's even easier. That's just 16.8. 16.8 meters per second, just meters per second. And then so x2, so when they are, when he's slowing to rest, we know the initial velocity and the final and the acceleration. So x2 minus x1 equals, well, just do the third, solve for displacement in the third kinematic equation, and that is V2 squared, V2 squared minus V1 squared, I keep wanting to raise to the 0 power, divided by 2 times A1. This is just the third kinematic equation. Solve for delta x. And so this, I don't know off the top of my head. This is, maybe we can inspect it and find some tricks in it. Or just plug it in, minus 16.8 meters per second quantity squared divided by 2 times 1.68 meters per second squared. I don't know about you, but I think we can factor out a 1.68. This is like, that's like x squared divided by 2 times x over 10. That's equals, doesn't that just equal 5x? So isn't that 84? Whoa. Again? Let me just a minute here. It's looking like the distance traveled when they slow down is the same as when they sped up. It looks like the total distance traveled is 168 meters. That might make you want to question what you did. I think it's fine though. And it looks like we don't have time for that last homework question. So I'll start 6.65. I will do that next time. That'll be the first thing I do. But yeah, this is another example problem. This is another good practice problem where once again, and here's the theme. I mean, before we're all gonna split up, is that we use forces, as you can tell, we use forces to find out how an object's motion changes. That's the whole point of Newton's second law, is to use forces to understand how an object's motion changes. Because once you know the acceleration from the forces, then you can do all the kinematics stuff that you want to get find out how far, how fast, how long, whatever. All right. So any questions or comments before we break today? Let's see. The acceleration. Oh yeah. Acceleration different when slowing down. Yeah. I guess so. So it shouldn't be. Yeah. So it shouldn't be. Okay. Before I go offline, let me just double check that. You're right. That was something that was an issue. So that is wrong right here. So this is really, and that's all true, but that's not valid for this problem. So that was like supposed to be the 0.98 meters per second squared. And so yeah, you will get something different. I apologize for that. Good catch. You guys are a little bit more on it than I am, I guess. The fact that you guys said you guys are in the classroom doing it kind of threw me off. So yeah, it will be a different one, and I won't work that out in detail, but you can find that. Yes, so that was a question in the chat about, shouldn't the acceleration be different? Absolutely, it should be, in fact, be the 0.98. So actually, let me save that instead. All right, so if nothing else, I want to thank everyone for attending. So we're still going to do this tomorrow and for Friday. It'll still be online, I guess. If you guys want to show up in the classroom, if you guys want to work it out yourselves, it's fine with me. But I'll be here. I'll be in my office at my house. So yeah, let me stop recording.